welcome to RF transceiver design course. We have already discussed about the active components. Now we are going to discuss a passive components and impedance matching in this module 5. Uh, if we see the RF transceiver design, more than 50 percentage of the transceiver design is about the passive components. So, we will go through the detail about the passive components and impedance matching in module 5. So, we if we start designing a high frequency RF circuits, what are the problems associated with high frequency design? At high frequency design, circuit dimension becomes comparable to wavelength at microwave or high frequencies, and that will, because of that, you need to consider the signal not as a just electrical signal, but it will behave like a waves. So, it is more like a waves, and there are at high frequency circuit elements become more distributed rather than lumped. We will also see some example of how to differentiate between distributed and lumped element. Uh, at high frequency, another important effect, that is a phase effect. So, phase effect is also more apparent. With small lambda, signals at different points along a line are no longer in phase. So, if we take an example of a differential amplifier, and if for example you are not getting a 0 and a 180-degree phase shift, then there are more feed through and your CMRR will reduce. So, phase effect is also more apparent in the high frequency design. At high frequency, you will have more parasitics effect. We already have seen many capacitor associated in the BJT and MOSFET in active device, and there are inductance also, stray inductance will also be there, and when you are connecting, there is a capacitance in the cable link. So, when you connect one line to one component to another component. And the final is a skin effect, because at high frequency your wave travel on the surface of the conductor, and because of that there is a the cross sectional area will reduce and it will increase the resistivity. So, that is also important while considering the high frequency design. For that, some of the high frequency what are the effect that will come when we design a high frequency component, and mostly the transmission line, that is important to study. So, if we try to define the different regime, there are three basic regime based on the dimension, because when we are designing a RFIC, the dimension are less, and but if we are going for very high frequency circuits, your dimension are much comparable to the wavelength. So, we need to see there are three regimes. First is a lumped circuit regime, where almost all the low frequency design you consider this, where inductor you consider as an inductor. So, in that your physical dimension is much less than the wavelength of the signal, because as your frequency is less, your wavelength is high. So, Maxwell equation you can easily simplify, and you can ignore the wave nature of the signal. You can easily use a Kirchhoff law, inductance and capacitance as it is. But there is another regime, that is the optics regime, in which your physical dimension is much greater than the wavelength of the signal. You can see that your LED light. Now, your LED dimension is much higher. Let us say if we consider the optical range, it will be 850 around 850 nanometer to let us say 1550 nanometer. So, if you see the dimension, physical dimension of the LED is much higher than the wavelength. So, in that case your Maxwell equation you can simplify, and your waves becomes a rays. So, you can consider waves as a rays. You can use a Snell's law, you can use mirrors and lenses and polarizer. As if you remember in the first class, I have explain Bose's experiment where his wavelength is a very less, and he has used all these mirrors, lenses and polarizer. Now, the third regime where most of the RF circuit designer will be, so this is very important regime, that is a transmission line or distributed circuit regime. Now, in that case your physical dimension is much equal to the wavelength of the signal, and in that case you cannot ignore the Maxwell equation. It cannot be simplified, and your waves are waves and transmission lines, microwave circuits, optical fibers. So, all these things you should consider. You cannot ignore the Maxwell equation. So, if we want to define the distributed versus lumped, there are three ways we can identify distributed versus lumped based on the rise time, means rise time versus the travel time, that how much travel distance between the distance and what is the rise time of your circuit. Then you can also define based on the period and travel time, and you can also define based on the component size and the wavelength. So, if you see the rise time, we all know that when your signal will have an amplitude rise from 0.1 of the output voltage, maximum voltage, to the 0.9. So, 10 percentage to the 90 percentage, that time is called as a rise time, and this rise time, and there is a TD, that is a travel time. So, that is given by the length or velocity of propagation. So, how much wave is propagating, that is a length of your transmission line. So, if you know that rise time TR and if you know the TD based on your length, then this is, you can get TR and TD, and based on the this is a design guideline, or let us say based on the experiment, it has considered that if your TR is TR by TD, if it is greater than 6, then you can consider it as a lumped. But if it is TR by TD where your rise time is high, then TR by TD is less than 2.5, when your rise time is reduced, then it is considered as a distributed regime. So, based on the rise time and the travel time, you can identify that you should consider the lumped circuit regime or the distributed circuit regime. Then there is another example, that period versus the travel time. So, in this example is taken from the reference book, and here this transmission line. So, this is a normal telephone cable line, or let us say you can consider the normal electric poles. Now, electric poles has a the frequency is around 50 or 60 hertz, and your period will be, you can find out which is a very high. So, now if you find the TD which is L by V, same as this, and T which is 1 by F. So, if your TD is less than 0.01 T, it is considered as a lumped circuit regime. So, if you take this example, it will roughly come, if you consider a 60 hertz of frequency, it will come roughly as a 50 kilometer. So, for that much wide distance, you can consider the lumped regime. You should not, you do not need to consider distributed, because your frequency of operation is less. Now, third is very important, and all the RF designer will use, that is the component size versus the wavelength. So, your wavelength is a speed V by F, that is a speed of light by frequency, and based on that you can find L, that is a length, means what is the size of the component, which if it is a less than 0.01 lambda, it is considered as a lumped circuit regime, and if it is less than if it is greater than 0.01 lambda, it is considered as a distributed regime. So, here based on the component size and wavelength, we can consider it is a distributed or a lumped circuit regime. We will take one example because that is widely used in the RF circuit. So, if your maximum frequency, if we define based on the rise time, that is given by 0.35 by TR, and this is commonly taken as the highest frequency of interest because all the digital circuits and there are all the clocks considering the rise time, and your corresponding to f max you can write lambda short based on V by f max. So, if we take a distributed regime, your physical length L, which is equal to lambda short much less, which is around 0.01 of lambda. So, then it is a distributed regime if it is coming in 0.01 of lambda short. So, for example, if your maximum frequency based on this equation is 30 gigahertz in air and your lambda short, if we calculate, is a 10 millimeter. So, your length should no more than 100 micrometer. If your length is more than 100 micrometer, then you should consider the distributed regime. It is no longer a lumped, and 100 micrometer is too small, means our normal chip size is also 1 mm square. So, inside the chip also you should consider the distributed regime. And one more thing I want to add, that is the speed of EM waves in PCB or in semiconductors is different, less than the speed in the air. So, if it is a 30 gigahertz, if you consider it is in PCB normal, that is a 14 gigahertz. Sorry. So, this is a distributed versus lumped, and when you should consider the lumped regime. So, mostly because nowadays we all the digital analog circuits, RF circuits are operating at very high frequency, and here if you consider the rise time, generally it is in picosecond. So, that is frequency is too high, and in that case we should consider the distributed regime. So, it is important to learn the transmission line. So, there is one example on right side is there, that is if there is a block A, you have some block on chip, that is A, and there is another block on chip B. Now, high frequency signal is travelling from X to Y. So, this is a transmission line, and let us say if you consider if it is on PCB, if it is more than 10 centimeter or more, then you should consider that it should means you should consider the effect of transmission line. So, same thing if you want to avoid, let us say in the second example, there is a block A and block B is connected through the transmission. So, if there is a block A which is connected to the block B and there is a transmission line, means through the wire. So, wire is also considered as a transmission line. So, if this block B is not matched properly, then there is a reflection of the signal occur, and we will discuss about how the transmission line work in this lecture. So, this is very long line. If we try to model the long line into the small short portion of the transmission line, it can be modeled with the delta Z, means very small distance, and the distributed components over the transmission line is mentioned in series. It is R delta Z, L delta Z, where R is the resistance per unit length, L is the inductor per unit length, G is the conductance per unit length, and C is a capacitor per unit length. So, if you find a voltage at Z comma T and at Z plus delta Z comma T, we will try to solve the voltage and current for this transmission line. So, if you try to if you use the KCL and KVL, you can use the KVL in the same circuit, which is VJT minus R delta Z IZ comma T, L delta Z del IZ comma T by del T minus Vz plus delta Z comma T equal to 0. Same thing you can use for the capacitor. Now, if you divide above equation by delta z and take the limit delta z tends to 0, you will get del I by del z t, which is r I z comma t minus L del I z comma t by del t, and you will get a del v. So, so this is a same equation you can mention in terms of del I and del v. So, this equation is called a Telegrapher's equation, which is you can write based on the transmission line KCL and KVL. If you try to make del V z comma t by del z, which is equal to minus r plus j omega L I z, and del I z by del z, which is minus c plus j omega c V z. Now, if you again differentiate this with the same with del by del z, if you differentiate this by del z, you will get the equation which is del square V z by del z square minus, that is combination of r plus j omega L g plus j omega c, that is the gamma square V z is equal to 0. And same thing you can also get for the current del I z by del square z minus I square z, which is equal to 0. Here gamma is a alpha plus j beta, and it is given by square root of r plus j omega L and g plus j omega c. So, gamma is a propagation constant, where alpha gamma is divided in two terms, which is a alpha, which is a attenuation constant, and beta is a phase constant. So, your attenuation you will get by alpha, and beta will define the phase. So, this is a normal wave equation. The solution of wave equation is already known. You can write a voltage and current, that is at any distance z, Vz, V0 plus e raised to minus gamma z, V0 minus e raised to plus gamma z. So, always remember that this minus correspond to the wave traveling into the positive direction, it is an incident wave, and this gamma is plus gamma represent wave traveling into the reverse direction or the reflected wave. So, here V0 plus is nothing but incident voltage, this is an incident voltage, and V0 minus is a reflected voltage. So, same thing you can also write in terms of current, and this current also if you if you divide with the impedance, then you will get V0 plus, you represent current also in terms of V0 plus and V0 minus. So, your Z naught is given by r plus j omega L by gamma, which is equal to r plus square root of r plus j omega L by g plus j omega c. So, this is a very important equation. This is called a characteristic impedance of transmission line, and characteristics impedance of transmission line will define for each transmission line, and it will be the same throughout the transmission line. So, you can write Iz in terms of the V0 plus and Z naught, which is e raised to minus gamma z minus V0 minus Z naught e raised to gamma z. So, there are special case of transmission line, that is the lossless transmission line. In that case, your R, which is equal to G, is equal to 0. So, your resistance and conductance is 0. So, there is a only phase difference, there is no attenuation. So, your alpha will be 0, only there is a j beta. So, beta is given by omega under root LC, and attenuation is 0. This is a special case of a transmission line, and your Z naught, which is equal to square root L by C. So, the general solution again you can write in terms of beta for lossless line. So, this is a e raised to minus beta z, and this is e raised to plus beta z. Similarly, the gamma, because alpha is 0, the gamma there is a replaced with the beta. So, your wavelength and the phase velocity lambda, which is a function of beta, is given by lambda, which is a 2 pi by beta. You can represent in terms of 2 pi by omega under root L c, and your phase velocity is given by omega by beta, which is equal to 1 by under root L c. So, this is related to the lossless transmission line. So, now we always, because we are not going to use a transmission line just open, we are going to terminate it with some load, and that is important. So, if you terminate it with some load, then what will happen, that there is a this is a Vz, that is V0 plus e raised to minus gamma z plus V0 minus e raised to gamma z. Your ZL at this node, that is length when it is 0, you can write V0 plus V0 minus by V0 plus minus V0 minus into Z0. If you write in terms of the current Iz, then there is a V0 plus by Z0 e raised to minus j beta z minus V0 minus by Z0 e raised to j beta z. If we define one parameter, that is a reflection coefficient gamma, the relation between the reflected voltage by incident voltage, that is V0 minus by V0 plus, which is equal to ZL minus Z0 upon ZL plus Z0. So, same equation, based on the same equation we can write it, the reflection coefficient gamma, which is ZL minus Z0 upon ZL plus Z0. So, this is very important parameter as far as transmission line is concerned, that you can identify that how much amount of power is reflected back, what is a voltage that is reflected back. So, that is defined as a ZL minus Z0 by ZL plus Z0. So, the voltage and current on the line, it is a consist of a superposition of a incident and reflected wave, and there are a standing waves which is generated because of combination of the incident and the reflected wave. You can write Vz and I in terms of beta. Now, the average power, so based on the voltage and current you can get the average power. So, average power is half real part of Vz conjugate Iz. So, if you put this equation and if you just consider the real part, it is a 1 minus gamma square. Now, this is a power that 1 gamma is the quantity which tells that how much power is returned, and that is defined as a return loss. So, based on the gamma you can define the return loss. So, loss in the power due to mismatch, because when gamma is not matched, means when your impedance is not matched, there is a reflection, and due to that there is a loss. So, loss in the power due to mismatch is called a return loss, and return loss is defined as a minus 20 log of gamma. So, what is the ideal value of gamma? So, gamma is ZL minus Z0 by ZL plus Z0. If your ZL is equal to Z0, what is the ideal value? That is a 0, reflection coefficient ideal value is 0. So, in reality getting 0 is not possible. So, all the designer or all RFIC designer or microwave designer will try to consider the value of gamma which is equal to 0.1. So, means we cannot get the 0, but if we can get the reflection coefficient of 0.1, then return loss will come around 20 dB. So, if your return loss is 20 dB, that means your 90% of power is transmitted, only 10% is reflected, which is a non-ideal condition. So, you should consider getting the 20 dB of return loss, and you will get reflection coefficient of 1 when you have a complete reflection. So, it will come under the case of the open or short circuit transmission line. So, we can also measure the standing wave ratio, that is a maximum voltage V max. So, if you write a maximum based on this equation, the maximum, that is V0 plus 1 plus gamma, and minimum V0 plus 1 minus gamma. So, that is a sending wave ratio. Now, if we try to find the input impedance Zin based on the voltage and current equation. So, if we work around and if you try to find the impedance Zin at distance of minus L, you will get Zin which is equal to Z naught ZL plus A Z naught tan beta L by Z naught plus A ZL tan beta L. So, this is very important equation because you can easily get the input impedance Zin of transmission line when there are certain load ZL is connected, and all the microwave or RF circuit designer is using this equation to find the input impedance at the one side of the transmission line. So, there are two special case we will try to consider of the two extreme case for the load ZL load, which is a short circuit and open circuit. So, if your load ZL which is equal to 0, that means it is a short circuit, you have a maximum current. So, your IL is a maximum current. So, and your VL is equal to 0. So, if you write L is equal to 0 and ZL is equal to 0, in that equation your Zin input impedance is equal to JZ naught tan beta L. So, if you try to plot the voltage, so at voltage at the distance Z is equal to 0, it is 0, and at voltage which is at current which is a maximum. So, the current is maximum. So, this is considered as a, this is a sine kind of function and this is a cosine function, and this current is behaving like a cosine function and a voltage is behaving as a sine function. So, the difference between sine and cosine, that is voltage by current, will give us a tan beta L. So, you can also understand graphically or the mathematically, but when you see the tan graph, there is an important consideration is coming. One is when there is a at distance x, distance is equal to 0, if you just travel lambda by 4 distance. So, here it is a short circuit and at lambda by 4 distance it is a open circuit. So, this is a special case of a transmission line. If your length is just lambda by 4 line, your impedance will be inverted. So, your short circuit will be open circuit. So, you can write for L which is 2n plus 1 lambda by 4, your input impedance is equal to infinity. And there is another special case, if it is just travel the lambda by 2 distance, the impedance will remain same and it is a short circuit. So, in the most of the RF circuits or even in microwave circuits, the lambda by 2 line is an important line, and in that what will happen, if you consider the lambda by 2 length of the line, even on the on chip, when you are considering the length, if you have considered lambda by 2 line, then your impedance will remain same, there is no change in the impedance, whatever is the load impedance will come at the source. So, for L is equal to n lambda by 2, here it is Zin is equal to 0 because you have considered the short circuit. There is another case, that is a open circuit load. So, in open circuit load, if ZL is equal to infinity, the only difference is your current is 0. So, you will have a sine kind of function and your voltage is maximum. So, your this is a cos and this is a sine. So, cos by sine will give you cot, and by equation also you will get the same. And when you try to define the cot, it is a this behavior. So, you can see that cot function at lambda by 4 line. So, here it is a open circuit, but at lambda by 4 line it is a short circuit. So, open will be converted to short, that is 2n plus 1 lambda by 4, that is Zin is equal to 0. So, that is also beauty of transmission line, you can convert a open to short and short to open just by changing the length of the line. And if you consider the lambda by 2 line, you will get the same behavior. So, your impedance will, if it is infinity, you will see the infinite impedance, that is a open circuit. So, these are the two special case of the transmission line. Now, these two special case can be used to match the impedance. So, how we can do that? So, if you consider the Z in, this is the input impedance, and if your length of the line is lambda by 4. So, here this is a, if the impedance transmission line impedance is a Z1, then RL plus j Z1 tan beta L by Z1 plus j RL tan beta L. Now, in this case your lambda by 4. So, if I will write a beta L, so beta 2 pi by lambda, and your length of line is lambda by 4, then this will come around pi by 2. So, which is a infinity. So, your 10 pi by 2 is a infinity. So, if you try to take this as a denominator, you will get a this is cancelled out, this is cancelled out, you will get Z1 square by RL. So, what is the condition? Your length of the transmission line is should be lambda by 4, and what we are interested to find the impedance Z1, which is a square root of Z0 into RL. So, let us say if you want to match the 100 ohm of RL, and if your Z0 is around 50 ohm, then you can easily find out a Z1, which is a square root of 100 into 50. So, you need to design a transmission line which impedance Z1 is equal to this, and your at frequency. So, you can get the lambda by 4 line based on the frequency of operation. Let us say your frequency of operation is 30 gigahertz. So, this is how you can use a quarter wave transformer to match your input impedance with the real load. There is a one limitation of the circuit, this method of impedance matching, that your output resistance RL should be real. If it is a ZL, which is a combination of real and imaginary, let us say real and imaginary, then you cannot use this method, because there is a square root Z0 into RL is coming. But in most of the circuit we have a real load, and for circuit it is easy to design this kind of impedance matching. We will discuss more about the transmission line and its effect in the next class. Thank you.